So for our first example of a triple integral to compute, let's take the tetrahedron whose vertices are just the origin and the standard unit basis vectors. So let's see, if I sketch this guy here, world-class illustration, it's going to be this one right here. So we've got I hat and J hat and K hat. I'm not a huge fan of the hat notation. Decorations put me off, but whatever, it's good enough for now. So let's see. So the first thing that we need to do is figure out, what are the bounding surfaces of our region, and this one I picked to be pretty basic. So on the one hand, we have the z equals 0 surface down here on the bottom, and then we have the x equals 0 surface over here, and then we have the y equals 0 surface over here. And it just remains to figure out what is the surface here where these ones are that's sort of clipping off the corner of the first octant here. So that actually turns out is going to be x plus y plus z equals 1. That's what that guy is. So I'm going to set this thing up doing a z integral first. And so I just realized, I didn't actually draw that big enough. So let's make it, whoa, got some wobbly lines going on here, folks. Okay, something a little bit bigger, and I didn't even like that one. That's too wacky. Okay, here we go. All right, so like that, and like that, and like that. Okay, thank heavens for curve straightening things. Okay, so I've got my upper surface, the formula for my upper surface, and so I'm going to set up my first integration going, and it's going to be for dz. So I'm going to be looking for where vertical lines first hit the region and then when they exit the region. And so if I drew a vertical line here, then, well, it wasn't quite vertical. There we go. Then it first hits the region right here, and then it leaves when it punctures the surface somewhere. Whoops, wrong color. I meant to use this one. Right up there. Yeah. So in other words, I'm going to be beginning at this surface. So just like before, we talked about like which curve do you enter on and which curve do you leave on. This time I'm going to be talking about which surface do we enter the region on, and then which surface do we leave the region on. And so then the one that we leave is going to be this entire upper triangular front sort of facing panel. Oh man, I never was good at coloring in the lines. Okay, that guy. Oh no, and then I just realized, you know what, I should have, let's call all this red so that it matches with my labels. Cool. Okay, so our starting surface down here at the bottom is where z is equal to 0. Our ending surface up here on the top is where z is equal to, and so I take this equation and I just solve it for z. So I get 1 minus x minus y. Okay, so now I have my innermost integral. We're going from 0 up to 1 minus x minus y, and we're trying to find volume, so we're going to be integrating the integrand 1. So let me just emphasize that's for volume. And then we did the dz integral. Okay, so that gives us the height of this surface above that green triangular region. And so now we need to look at the green triangular region. And so what you have to do is mentally project. Now, this was a simple enough example. We've done a lot of things like it, but just humor me and follow this thought process of imagining that you are like up here in space and you are looking downward right? It's directly from on top, and you're looking at the shadow that this region casts on the XY plane. And so what you see is something that looks like just this portion right here. And so let's set that up. So this is X and this is Y. This is the projection of E to the Z equals 0 plane. And so it looks like just a 45-45 right triangle. Let's see, where's, okay, close enough. So that's supposed to be 1 and 1 over here on the X and Y axes respectively. And now let's see, so we know if we are, you know, directly, if we're at some point in this XY plane, we know how high above us the plane is. That's given by the formula we just wrote down over here. But now we need to set up the double integral over this region. So let's see, so suppose we do the Y direction next. So we'll do dy. Then we're going to be going from, let's see, so we're going to start on this curve right here, which is where Y is equal to 0. And then we're going to end our slice on this curve right here, which is where Y is equal to, and you go, oh, how do I figure out what this is? Well, again, you might be able to tell what this one is just by staring or using your basic geometry, but the technique that you can always fall back on is that it's going to be the place where this and this intersect. So if both of those equations are true, then that means that 0 is equal to 1 minus x minus y. So x plus y is equal to 1. So that's my curve. And I guess actually here I want to save it, I want to solve it for y, because I want it in the form y equals for a y integration. So it's 1 minus x. All right, so then that tells me that my next integral, oh, I just realized I'm going to run out of room here. Let me bop that over. So we're going to go from y equals 0 up to y equals 1 minus x. Yeah, let me include the equalses in here just to make it super explicit. So this is z equals 0 to z equals 1 minus x minus y. Lovely, much better. Okay, so that's then our dy integration. And then as usual, we just have to say, okay, so where do we get all these slices? We get our first slice here at x equals 0, and our last slice here where we just nick the tip at x equals 1. So our outer integral there is going to be x equals 0 to x equals 1 dx. All right, there we have it. We've set up our very first integral. And then as you go to evaluate this thing, so we've got 0 to 1, 0 to 1 minus x, 0 to 1 minus x minus y. Notice two things. So just like mentioned in this last slide, z does not appear anywhere in these bounds. Y only appears in the first one, and x may appear in both of these, but definitely does not appear out here because that would be bad. Okay. The next thing to notice is that when we evaluate this first integral, we're going to integrate this z here, we're going to integrate this 1 here and get z, and it'll be evaluated from 0 up to 1 minus x minus y, which is 1 minus x minus y minus 0. And then this guy is exactly what you would have had if you set this up as a two-dimensional integral from the get-go. And in fact, if you go back and look at, oh dear, I'm not sure which video clip it is, but it's like one of the very first ones where we were doing double integrals. So like 15.1 or 15.2, somewhere in there. And you'll see that we, in fact, did this example, and this is exactly what we came up with in that situation. Now, you might say, okay, then if we could do that with double integrals, why do we need triple integrals at all? Well, what if the density of this thing is non-constant? So, you know, given by some formula like that, then the mass is going to be equal to the triple integral of this of this guy, and this cannot be solved as a double integral. Maybe solvable is the wrong word, but you can't. Well, yeah, you can't solve that problem with a double integral.